Welcome everybody to our post-Bayesian seminar series. As usual, these are important links that you can share widely if you want to. Two quick plugs before we start. As a reminder that we'll be hosting our workshop on post-Bayesian method at UCL London this May. So registration is open and we're accepting submission. The deadline is this Friday. So yeah, we are really excited to read your submissions. Also, Jeremiah's FX and Jax are organizing a satellite workshop at Basecamp this year. So we'll be focused on Bayesian computation and inference with specified models. So if you're interested, definitely check out the website for more details. So there is the QR code, so you can go to the website. Now back to the seminar. Remember that we are using the Zoom Q&A function for questions during the talks. Jan and I will be keeping the eyes on them and then passing to the question along during the break. So yeah. So we're still in chapter 1 today. We're almost done with chapter 1. Reminder, this is like a quick refresh of the structure. And today we have Professor David Dunson. He's an art and science distinguished professor of the statistical science and mathematics at Duke University. He's widely known for his influential work in Bayesian statistics. His work has been recognized with awards, including the COPS President Award and a gold medal from the US Environmental Protection Agency. So today, Professor Dunson will talk about robustifying Bayesian inference using coarsening. I'm really excited about hear more. So without further ado, I'll hand it over to you, David.
Yeah, thanks a lot. Thanks a lot for the invitation. I'm going to share my screen and then please interrupt me as we go. Yeah, so can you see it? Okay, great. So I'll first say that these are kind of old slides that I'm recycling. Jeremiah said to kind of give an intro to this kind of C-Bayes thing, coarsening. And so these are actually, I think, Jeff Miller's job talk slides at Harvard, and he's been there for a while now. And so I'll maybe make a few comments as I go through to update. But I think that Jeff made some nice slides, so it's all good. So yeah, I'll start out with a motivation, and I would just say my overall motivation and that of Jeff, which continues now. We've been working really actively lately, continuing these kind of coarsening ideas. Is that I like Bayes a lot, and I've worked a lot on non-parametric Bayes, and in that setting you have like almost too many parameters. It's not very interpretable, and so it becomes more of a black box. And so parametric Bayes models are really quite nice and useful, but the usual Bayesian paradigm assumes that the model is correctly specified, which is always wrong. And so how can we do something that like acknowledges model misspecification without kind of throwing out Bayes entirely? Like I would say something like a Gibbs posterior is kind of maybe going a bit too far. Like we'd like to still have a likelihood-based approach. We'd like to model the data. We'd like to be able to interpret the model parameters, but acknowledge some amount of misspecification. And so how can we do that? So even a well-chosen model will have some specification, and can we then do that in a way that maintains, like completely the Bayesian paradigm otherwise? And so, but it acknowledges some model misspecification. Okay, so that's the motivation, and I'll kind of go through that. We'll give one solution to that, which is this kind of coarsened posterior, and this is a general idea. The kind of Miller and Dunson version is based on kind of a Kolbeck-Leibler relative entropy kind of notion of coarsening. We've been working on other notions, Jeremiah and I and Mahir, Dewaskar, et cetera. We had a paper in JASA with one notion, and then we have another notion that's kind of underway that I won't talk about as much today, but we'll kind of focus mostly on the original notion. But this is kind of an active, interesting area of research. So starting with the original coarsening idea. Okay, so I'll give some toy examples, a bit of theory, and then time permitting, some more detailed examples. And again, please interrupt with questions or comments or complaints as we go. Okay, good. Yeah, so usually we assume that the model is correct, and so maybe then we do some sort of model assessments. We might do posterior predictive checks or some sort of model adequacy approach or goodness of fit diagnostics. Even if we do all of that, and we kind of do some sort of process to select a good model, the model is still going to inevitably be at least a little bit wrong. And in some cases, even small violations of the assumption of the model being exactly correct can have a big impact. There can be brittleness to model misspecification. And so in those settings, if you ignore that model error, then you might get really kind of crappy results that are very misleading. Okay. That particularly happens when we have some kind of model uncertainty, or if there's like a model complexity index, like how many mixture components do we have? Or what's the lag of an autocorrelation? Or how many latent factors do we have underlying the data? Or there's a gajillion predictors and then only, like how many do we include? And so when the model's wrong, sometimes the tendency is as you get more data is to kind of like include more and more terms, like more and more factors, more and more mixture components, more and more lags, more and more predictors, kind of without bound. And then you end up getting this kind of overly complicated thing that's just kind of trying to chase the true model. And maybe that eliminates the usefulness of a parametric model inferences. And so that's not good. And so is there a way to kind of combat that? Kind of acknowledge the models are wrong. So can we do it in a coherent way? Yeah. And the model averaging doesn't really solve the problem, because in model averaging, what you do is the typical notion of model averaging, you have a list of models, but all the models are wrong. But usual model averaging assumes that one of the models is right. And then as the sample size gets bigger, you're going to put posterior probability going to 1 on the model that's closest to KL, to the true data generating model. And that doesn't really do a good job either. So one of the contexts in which Jeff and I's kind of see Bayes has been very, very successful, I would say, is in mixture models. And so it's been used a lot since the original paper. And so in the mixture model setting, it's sort of the basis for model-based clustering. And so we say, oh, we like maybe have a mixture of Gaussians to characterize the data. And so you might use that mixture of Gaussians to do basically Bayesian density estimation, but often it's very, very, very often used for clustering. And so in practice, you could say like, okay, well, maybe the data distribution is like this. So it looks like in the univariate case as an illustrative example. And so maybe it is looks like maybe there's 2 clusters in the data, but they're not exactly Gaussian. Maybe the truth that we've simulated is skewed Gaussian. Okay. And so but if you looked at the data, you might be apt to just fit a mixture of 2 Gaussians here. Okay. And then but there's going to be some amount of misspecification. So if we do the usual thing, what we would do in terms of Bayesian inferences, and we would allow freedom in the number of clusters, and we actually had this blue line as the true data generating distribution, and then we fit a mixture of Gaussians, then what will tend to happen is as the sample size increases, we're going to kind of break each of these clusters up into like more and more and more kind of Gaussians to kind of fit the data distribution. Okay. And so you can kind of see that here. And so the standard usual posterior, where we free up the number of mixture components, as the sample size increases, we end up getting this kind of more and more components to fit the data. Okay. And so the one thing is that there's kind of a difference between components needed to fit the data and like what we want to do, which is kind of get a couple of well-separated clusters. Okay. But and so you could think like, well, maybe instead what I could have done is, I'm worried about this, so I might try to use a more flexible kernel for the data in each cluster. But what happens is that there's a pitfall there. Like as I make the kernel characterizing the distribution of the data within each cluster more and more flexible, my model identifiability gets worse and worse. There's been a lot of really wonderful work in recent years. I've mentioned particularly Long Nguyen at University of Michigan, and his former student Nat Ho, who's now at Texas Austin. A number of other people who've studied this problem of like, okay, we have a kernel mixture model. Now we're trying to infer the mixing measure, which is putting a weight on the clusters, and then also where the clusters are located. And even in a Gaussian case, as we go from a multivariate Gaussian, which is like spherical, to full covariance, the identifiability gets worse and worse. And so we can't really, in practice, use a flexible kernel in a mixture model because then we're going to have like really crappy performance in inferring the clusters. And then one instantiation of that is going to be terrible mixing of an MCMC algorithm. And so So we're sort of forced to use a simple kernel, but the due to this identifiability problem. But if we use a simple kernel, then we're going to sort of inevitably get over clustering because, the true biologic or scientific clusters in the data aren't going to exactly fit some simple kernel like a spherical Gaussian. And so what can we do in that case is what was one of the kind of initial motivations for this kind of C-Bayes formulation. Okay, so more generally, what we could think about, which this would also include the mixture model case, is that we might have some sort of true distribution that generated the data, P naught. And we have this kind of sequence of model classes. And so we have some model class M1 and then M2, which is a bigger class, and then we kind of keep making it more and more flexible. So you could think maybe M1 in the mixture case would be like a mixture with one component, and we add another component, we add another component. And so we're sort of like, well, if the true density is something like, that doesn't exactly correspond to a mixture of Gaussians, then what you'll tend to do is like you'll add more and more and more and more and more and more components to try to decrease the Kullback-Leibler gap from your model class to the true class, and then you'll kind of make your parametric model overly complicated, which will then, in the clustering case, lead to kind of not very useful clusters. But this also happens in general for lots of problems where we have some sort of freedom in our Bayesian model to choose the complexity of the model. Okay. So, okay, yeah, again, so I mentioned this in the mixture case, but if the model's wrong, why not fix it? Well, probably the true data generating model is really pretty complicated. And so by fixing it, we might need some very, very heavily parameterized model. We might need something that one might call Bayesian not-parametrics. And in that case, we kind of degrade a couple of things. The first might be the efficiency of posterior computation, but also the interpretability is going to decline. Another reason is that it's kind of hard to find good models in particularly complicated settings. And so, goodness of fit methods are not, that's like actually a pretty big gap in the literature of Bayes, I would say, is like good methods for goodness of fit assessments. Jeff Miller and I were both at a workshop in Columbia, and he had a really cool new idea on goodness of fit assessments using uniform parameterizations, getting so-called U values to try to improve on posterior predictive checks. And so that's just a note that, we don't have great methods for like, I have some complicated data. How do I like systematically explore the space of possible models to find a really good model for those particular data? That's hard. And so it might be that, well, we get a model that's kind of roughly close, and it's interpretable. That might be good enough. Yeah. Anyway, obviously we would like to get a simple model and allow it to be a bit wrong. And so what can we do? Well, we could do some some sort of robustness inferences, and this is like a not up to date because this is older slides, but some notions are Gibbs posteriors, and so we could focus instead on loss-based inferences and just like throw out the likelihood entirely, and then like, okay, well then we're going to be robust to misspecification of the likelihood. We could instead have some sort of really complicated model like Dirichlet process mixtures or Gaussian processes, got kind of very, very heavily parameterized models. And there's also some other notions of different types of robust approaches. There's Bayesian methods based on method of moments, more based on quasi likelihoods. You kind of throw out a regular likelihood, you replace it with some sort of more robust alternative. There's a lot of different methods one could use. A lot of them are sort of ad hoc and mostly justified, not really from a Bayesian perspective, but more you might be like, okay, well, I have this thing which is not really quite a posterior. It's some sort of bogus, slightly sort of posterior that I'm kind of use as a posterior, as an alternative to posterior. And then I might justify it by frequentist asymptotic arguments, like, oh, at least it like concentrates asymptotically on the right thing. And then maybe ideally it also satisfies some sort of BVM result. And so it gives me good uncertainty quantification. So a lot of the work has been done like that. And so we were particularly interested in, well, can we come up with like actually kind of Bayesian approaches that don't really rely in their justification on frequentist asymptotics. Okay, so what do we do? So we have this kind of coarsening idea. Okay, so I'll go a little slower here, try to get this idea across. And so we have some model class, P of theta. Okay, theta lives in some parameter space, capital theta, and we have a prior pi of theta for those parameters. Okay, and so now we're going to introduce, and so like you could think like if P naught is the true distribution that generated the data, okay, then like, and we're living in the class of all distributions, well, like usually like the parametric model is going to live on some sort of measure zero subspace. And so we kind of express that with this curve, okay? And so we have this P0, that's a true data generating measure. And we have this curve, which is like, all our data generating distributions in our parametric class, okay? And then we have points along that curve with corresponding different parameters. And so we're going to introduce the idea of a theta I. And so this is the idealized distribution of the data. Okay, so this is like some notion that theta I is the true state of nature about which one is interested in making inferences, but we don't have direct observations of these from this idealized data distribution, but we can imagine there to be some observations capital X1 to Xn, say that are IID from this P theta I. Okay, so these are like, in practice, it would be if we observe this idealized data, which are like actually directly from our, assumed model class, then we could just do regular Bayesian inferences based on updating, get the prior pi of theta with the data X1 to Xn, capital X1 to Xn. Okay. Well, in practice, we're like, okay, well, we don't really observe capital X1 to Xn. Let's say we observe a slightly corrupted version of X1 to Xn. So little X1 to Xn. Okay, and so these are corrupted, and so that kind of is allowing for the model misspecification. And so we're going to do it in the sense that the empirical measure of capital X1 to Xn is close to the empirical measure of little x1 to xn. So we actually observe little x1 to xn, but we're thinking that that distribution is close to the distribution of idealized data that are sampled from our parametric model, okay? And the closeness is measured in terms of like a distance. We need some sort of statistical distance between probability distributions. And then we also need some sort of radius, that controls the amount of misspecification. And so as we choose different distances, that's going to control the robustness properties, okay? And so we're going to choose like a KL type distance in this initial C-based framework in developing practical methodology, but this is a general notion, okay? And in work with Jeremiah and Mahir, it just came out in JASA, we were focused more on developing methods for like something like a total variation distance. And we have a paper well underway where we can kind of develop methods for like a Wasserstein distance here. But it's most simple. And in those other cases, we end up with a kind of different property, a bit different properties. Like in the total variation case, you can have a small proportion of outliers that are like corrupted, like super far away from the data, and then the rest of the observations sampled exactly from your model. You can deal with settings like that. Okay, but this is the basic setting so far, is to like develop this kind of conceptual model where we're allowing misspecification in this sense. Okay, so we have this, we introduce this idealized data, and this the true data distribution is close to that of the data from some sort of idealized data that are sampled from your actual parametric model. Okay, so if there was no corruption, then we should just use the standard posterior, which would say, oh, well, that's the posterior distribution conditionally on the event that the idealized data is equal to the observed data. Okay, and so if there's no corruption or misspecification, then that would be totally fine. But if we either have model misspecification, or as we can kind of think of as corruption, then we don't want to do that, and we instead condition on this this different event. So we define really a Bayesian posterior but instead of conditioning on the event that the idealized data is equal to the observed data, we condition on the event that some discrepancy or distance between the distribution of the idealized data and that of the observed data is less than some radius r, okay? And we can put a prior on R, and we'll do that in practice. So we can say that, oh, well, R is unknown, but we give it some prior H. We might not be able to, like that's sort of an open problem, is how to best maybe choose the hyperparameters in H that might have an impact on the eventual coarsened or C-posterior. And that's a really interesting problem that we've thought about a bit, but I don't think there's yet a super elegant solution to. Okay. So yeah, and so like more generally, we could just consider some sort of discrepancy between the two data sets instead of between the empirical measures. Okay. Yeah, so this is the basic setup. And so it looks kind of familiar. Like if you look at the C-posterior, it's like looks very similar to the posterior resulting from ABC. So for in ABC, what would we do? Like, well, we would sample. Maybe we might like old school ABC. You might sample from the prior, and then sample data from the prior predictive, and then if the data from the prior predictive is close, according to some sort of discrepancy, summary distance between summary statistics or some such, to the data that we actually observed. And so we could think, oh, this in that ABC setting, the capital X would be maybe data from the prior predictive under our parametric model, and then x 1 to xn, little xn 1 to xn is the observed data. Well, if the discrepancy is small, then we accept that draw, and that was be an old school way to sample, do ABC sampling. And then, so the ABC sampling is motivated by the intractability of a likelihood function. We can't write down the likelihood, but it would also have a robustness property, which I think certainly people didn't realize very much until recently. And so because they're like, oh, this is actually bad, that we have to like have some sort of approximation error to we actually want the posterior of theta given x1 to xn sampled, thinking exactly that the data are sampled exactly from our presumed model, but we can't write down the likelihood. And so we reluctantly define this kind of alternative posterior, and then but we really want to kind of make R really small, and so like our approximation error is small. And so whereas from our perspective, you could think, well, the ABC there might be like a win-win in that the likelihood, we don't have a likelihood, but we also can kind of robustify inferences to model specification by not making R really, really small. Yeah. And so there's been a lot of work on ABC, but yeah, the motivation is completely different, of course. Okay, so so some sort of pros of this framework. Well, so you're going to be robust to small departures from the model. It's going to inherit the properties of the distance, and so you can kind of control by choosing your distance what type of robustness you want, which is kind of nice. It's coherent Bayesian approach. It's like a real posterior, but it's based on some limited information. And that limited information is very elegantly posed, I think, because it's sort of like one right way to think about it, in that, okay, well, if I have model misspecification, then I don't actually get data directly from my presumed model. And so I maybe get data that are like close to being from the presumed model if the model is pretty good. And so in that sense, like I don't really even want, as my sample size goes to infinity, I don't want that posterior to like keep concentrating on some sort of single point, like that. People often do that in the case of model misspecification. They're like, oh, well, what happens? Like my true model is P naught over here, and then I'm in some parametric class, and then, okay, well, as the data gets bigger and bigger, I concentrate on the minimal KL point. You can call that the pseudo true parameter value, like theta star. Well, my posterior distribution is going to concentrate on that point, and then the asymptotic covariance is going to have some sort of sandwich estimator form. And so if I don't allow for the misspecification, I'm going to get the wrong asymptotic covariance, but I could adjust it using a sandwich estimator. But still, like, it's going to concentrate more and more and more, and then really I'm doing inferences on that pseudo true parameter value. Like that's not our view. Like really we're saying that if you have misspecification, I don't really want to do inferences on that pseudo true parameter value. I want to do inferences on the parameter in this kind of idealized data distribution. Um, and so from that perspective, I don't get data directly from that distribution. I just get data in some small neighborhood. And so even if my sample size goes to infinity, my coarsened posterior isn't going to keep concentrating. It's just going to kind of it's going to concentrate to some level and then not concentrate anymore. And so oh, we don't like that. Like, because a lot of people are just obsessed with frequent asymptotics and they're like, oh, well, what's the concentration rate? And it's going down and it has consistency and everything. And so this is being fully Bayes characterizing model uncertainty, but it's not actually going to keep concentrating. It's going to, even if your sample size goes to infinity, we have limited information about the parameters in the true data generating model due to the model misspecification. And so that's just sort of like a characteristic of the method, which is really interesting and makes it interesting to think about theory justification because we don't have things like the posterior just like concentrating on one point asymptotically. Okay. We can, yeah, it's coherent Bayesian inference. If we choose a relative entropy choice of D, then we obtain a really, really simple form for the C posterior. That's only going to allow for certain types of model misspecification that correspond to relative entropy. And so, yeah, as I mentioned in kind of ongoing work, we're developing methods that are more broad, like that have different types of Ds. And in some cases, those lead to like local weighting instead of global weighting. Okay. Yeah, so what would be like the cons? Well, what I'd like that we don't have yet would be like, well, what if I have a bunch of models and well, what I would like almost like adaptive behavior. For example, let's say suppose the model was perfectly specified, then I would like to somehow choose that distance to like collapse in that case where it's perfectly specified so that it becomes equivalent to a standard posterior, like adaptively. And so to do that, we would need to have some way to like consistently estimate the neighborhood size, and which relates to minimal deviance estimation type problems. And so there's sort of an open research area of like how to kind of combine some sort of minimal deviance problems with C-based type frameworks. So you could kind of collapse and then actually get complete concentration if the model was perfectly specified. And also, can we do that in a setting where we're like use C-Bayes and model selection? It would be like, well, it's sort of more coarse for models that are more misspecified than others. Like how do we kind of how do we kind of do that? And we can use C-Bayes for model selection within one framework if we just have a model selection index, as I mentioned, like the number of mixture components within a single encompassing model, then it works. But some of these kind of automated concentration neighborhood size issues remain to be fully worked out. Okay, so relative entropy C posteriors. Okay, so there's a lot of choices of discrepancy or distances that we could use. Maximum mean discrepancy, Wasserstein, blah, blah, blah. It tends to be that the relative entropy works out really nicely. We particularly found that in this, as I mentioned, this work where we were trying to extend the set of discrepancies to include total variation in other cases. Then we found that the computation becomes really, really hard. And we had this recent JASA paper just focusing on the likelihood type approach, which kind of leads to local weighting instead of this global weighting that we'll get in this case. But so the relative entropy is sort of like a particularly nice case, but it's also somewhat limited in the type of discrepancy we're going to get. But anyway, so let's go with relative entropy. Okay. And so we're going to suppose that d little n, the discrepancy between our idealized data, capital X 1 to n, and the actual observed data is some consistent estimator of the deviance deviation between p naught, that's the true data generating model, and p theta. Okay. And then we have the xi's are IID from p theta, and the little xi is ID from p naught. That's the true data or IID from the true data generating distribution, which is unknown. Okay, and then we're gonna choose an exponential prior with some key, very, very key parameter alpha for the neighborhood size, the degree of discrepancy. And so then you can come up with a asymptotic approximation, which leads to this really cool power posterior. Okay, and so then the coarsened posterior is going to be proportional to the prior times a product likelihood. So if we just had the regular fully, like if there was no misspecification, then we're focusing on like product likelihood. So the posterior would just be proportional to pi of theta times the product from I equals 1 to n of p of theta of xi, and there would be no zeta n power. Okay. But when we put in the coarsening, the effect of the coarsening is going to put in the zeta n power. Okay. And the zeta n, using this kind of nice asymptotic approximation, is just going to have this this form of 1 over n divided by 1 over n plus 1 over alpha. Okay, where alpha is that kind of neighborhood size parameter. Okay, and a nice thing, the reason that C-Bayes has been so popular, I think, is that you can imagine that if I had some sort of posterior sampling algorithm to target the regular posterior, then probably I can like easily come in and throw in these zeta n powers, and that, like for example, if it's an exponential family, I just pull the zeta n's into the likelihood, and then I could just use whatever computational algorithm that I used in the regular case would be easy to modify to allow these kind of power terms on the likelihood. Okay. Yeah, so it's really easy to use in that case, and it's a simple modification. And I would say also, like, it relates, there's a big literature on power posteriors that, often that aren't motivated by the same, and they're never motivated by exactly the same setting, but power posteriors have been widely used with other motivations, some including robustness, others to include historical data, but downweight the data, to decrease, to improve non-parametric Bayesian approaches in terms of like the assumptions that we need to show posterior consistency. It tends to be, if we raise the likelihood to a fractional power, that it makes it easier to show posterior asymptotic results. So there is this literature on power posteriors that relate to this, initial Miller and Dunson C-Bayes approach. If we use some other neighborhood, we might have some other form for the C-posterior. Okay, so one key question is, how do you choose the precision? And so this is sort of like the key parameter controlling the degree of model misspecification. And I mentioned this earlier a little bit about there being this kind of open area, like where I'd like to kind of like have an approach that maybe allows me to infer like how close my parametric family is to the true data generating model. And maybe I can like use some sort of empirical Bayes estimator. Then if I could get some sort of estimator of that discrepancy, it seems like that's going to have to rely on, maybe I get some sort of non-parametric kernel density estimate for P naught. And then now I have my estimate under my parametric model, and now I'm trying to estimate that discrepancy. So it becomes kind of complicated, and then subject to the coarse dimensionality and other things like that. And so our initial strategies are to do something simpler than try to actually estimate how far your parametric model is from the true data generated model. Okay. And so what are the strategies? I mean, I think this one strategy is to it's sort of like, if you think about it, it's somewhat of like an related to like an asymptotic sample size. So we could just set the mean neighborhood size to match the amount of misspecification we expect. That might be difficult because, like, well, how much do we expect? I don't know. So strategy two, I think, is a bit more effective than strategy one. And that is, strategy two is to be robust to perturbations that would require at least n samples to distinguish. And so you're like, okay, you can imagine that earlier example where I had the skewed, the truth was a mixture of two skewed Gaussians. but then my model that I'm fitting is like actually a mixture of Gaussians. So if I just, I could imagine plotting the histograms. And so like at what sample size, if I plot the histograms, can I like even like visually distinguish that like, well, those don't really look Gaussian. It looked like the plot I showed, you couldn't really tell that they were skewed Gaussian. They could have been Gaussian. And so um, if you choose alpha to be like that sample size, and you can even like do some exploratory analysis or initial simulations and things to kind of assess that. But it's sort of like at what point is the data large enough to have power to tell you that your modeling assumptions are violated? So that's a good way to think about alpha, I think. And so yeah, so that's a really useful way to think about it.
Wait,
Strategy.
David, can I ask a quick
Yeah.
question?
Yeah.
Could you also think about this a different way, where strategy two, you could say to yourself how many you would choose your hyperparameter in such a way as to say how many data would be required for me to be actually convinced of the opposite, and then go back to allowing concentration. Is this a considered way where you're looking to choose your hyperparameters then to solve that concentration potential negative you discussed earlier?
Um, yeah, I mean, I guess, yeah, I don't, I mean, definitely you could think like, I mean, what would be the sample size so that you have any power to detect lack of fit of your parametric model? I mean, if you could sort of formalize that, and then now I have that sample size and I want to back off of that. But is that what you meant? Or
More like, is there a way of choosing this then so that after a given sample size, you determine whether or not you would like to actually concentrate on your pseudo-true or not concentrate at all?
okay, I see. Yeah. Yeah. And so how do you choose that sample size then?
Yeah, no, I don't know. I was just
I mean,
wondering
I
if this
like
was
that. I
something.
like that idea that like, okay, well then, so you could turn it on its head. So if you had a sample size so that, okay, now it's big enough to detect departures from whatever your parametric model is, you have reasonable power to detect departures from that parametric model. Then maybe at that point you're like, well, if I do and I don't detect any departures, maybe I want to go with the regular posterior.
Yeah,
Yeah. Yeah, that's reasonable. Yeah. Yeah.
cheers.
Yeah, I mean, I think it's like an open area in a lot of ways. It's sort of like, I mean, again, the Gibbs posterior case, we have this key problem of like, well, how do we choose the kind of weight on the loss versus the prior, and that's going to control the posterior concentration of the Gibbs posterior. And there's been like that's been more worked on, I think. There's been like a series of papers by Ryan Martin and other people developing strategies for choosing that kind of parameter. And so in C-Bayes, that the alpha parameter is sort of as important in some sense. And I think there still needs to be some more strategies for choosing it. In practice, there's these kind of rule of thumb, but I would love to have more kind of like really theoretically rigorous. And we started going down this line with Yi Chen Zhu, who was a PhD student of mine, but then he left for a postdoc with Botan Zabo. Now he just got a faculty position in Hong Kong, and we sort of dropped the thread a bit, but we had some ideas, but yeah. Anyway, encourage some smart people in the audience to work it out for us. Okay, and so another strategy is there's this kind of heuristic, and so you could choose a range of alpha values, and then you can kind of come up with like a heuristic for choosing a reasonable alpha value. This was Jeff's idea. Okay, and we'll kind of get back to that. So here's just a little bit of, very, very, very incomplete and out of date review on power likelihoods. The usual power likelihood isn't like sample size dependent and doesn't have the form of power that we got automatically from the C-Bayes notion. But there's been a variety of, we can like anneal to improve MCMC mixing, or this consistency in nonparametrics. The first paper on that was by Stephen Walker and Hjort had this. It was very cool mathematical result. It's kind of interesting that, it's kind of bizarre almost that, okay, well, I have a non-parametric model and now I'm trying to show some sort of posterior frequentist asymptotic behavior. the model. And then it's a lot easier. I can do it under simpler assumptions if I just take the likelihood and raise it to like any fractional power, like less than 1, then I can reduce the stringency of the assumptions. It's kind of strange to think about. Joe Ibrahim has a ton of stuff on power priors for taking historical data. You raise it to a fractional power to discount the impact of the historical data in the current analysis. Those have been really, really popular, including to the current day. Yeah, I would note in particular, Grunwald has some beautiful, great work on using power posterior and actually to improve robustness from a totally different perspective, but kind of getting a related answer. So he has some really wonderful work. Okay, so let's give some examples. Okay, so this is a real kind of toy example where you can work out everything. So let's just say that the data are IID Bernoulli, and you're interested in testing the bias coin problem. Okay, so theta is a half versus theta is not a half. Okay, this is a simple example I give in my baby Bayes class for introducing Bayes factors and things like that. So we have a prior on the two hypotheses. Let's just say they're equal. And let's just give theta under the null. Theta is just fixed at 1/2, and so there's no free parameters. Under the alternative, theta is uniform 0, 1. I actually talked about this today in my Bayes class, but, as a remarkable coincidence. That was this morning right before this. Okay, so the standard posterior we can just calculate easily from beta binomials, and then we get this kind of this form where this is like the beta function. And then this is like the average, and then this is the sample size. Okay. And so if we let's suppose that the observed data is corrupted, and so we're not really for whatever reason, and then that now the coarsened posterior we can show is like has a very similar form, exactly the same form, but now we instead of n we have alpha n. Okay. And so how do we how do we choose alpha in this case? Okay, so in the strategy 1, we would set the mean neighborhood size to match the amount of misspecification we expect, and so we can sort of think about that in this case. It's a very simple case, and so it makes it easier to use strategy 1. And so we could say, suppose we expect the misspecification affect x bar by no more than some small amount epsilon. Okay. When theta is equal to 1/2, and then we do a chi-squared approximation, and then we can sort of back solve, and then we can get a particular value of alpha, which is 1250. And then you could also think about, well, that you could think about that sort of test inversion problem that we were sort of talking about, where, okay, well, this is the sample, like at this sample size, then we're starting to get power to detect this degree of misspecification. So you need a pretty big sample size if like the degree of misspecification, by misspecification, like even if it to detect departure from the biased coin assumption, we would need a pretty big sample size if there's only a small amount of discrepancy. Okay, so that's one strategy. Let's just sort of see what happens. And so and I'll show more interesting examples later. This is a very, very toy example. So if we suppose H naught's true, so it's an unbiased coin, but maybe the X1 to Xn are the observed data are corrupted and behave like Bernoulli 0.51. The C-posterior becomes robust to this, but the standard posterior is not. Okay, so you can see that. So this is like, as if we choose our alpha such that we allow that degree of misspecification, then, well, you can be off by, that's close enough to a biased coin, an unbiased coin, putting 0.51. And so then we just like take that into account in our degree of coarsening. And then we can see that, okay, well, what's the posterior probability of H naught given the data? So as the sample size increases, close to that sample size I gave on the earlier slide, they become very similar. And then after that, the standard posterior is like, okay, and so like it's sort of building up evidence of H naught that is an unbiased coin initially, and then the C posterior kind of keeps going up, but then like doesn't go up to 1. There's always some gap where we're not going to get posterior probability of like 0.99999 or something. Whereas the standard posterior, like, oh, at some point it's like, okay, now I actually have some power to distinguish 0.51 and 0.5, and then like, okay, well now I'm just going to kind of decide that it's a not an unbiased coin. And so it's kind of, you're sort of coarsening your inferences a bit, you know, so you're like being more robust to these small perturbations. And so it makes sense in a lot of settings. And so otherwise you get this sort of well-known, like as the sample size goes up, then like, well, everything becomes significant. Everything, the null is always rejected. And so by using the kind of C-based framework, you can kind of protect against that. Yeah. And so if the departure from H naught's larger than our chosen tolerance, then the C-posterior actually, so now it's 0.56, and then we've only allowed like 0.02 departure through our neighborhood choice. Then the C-posterior behaves more similarly to the regular posterior and actually favors H1. Okay, so it's kind of a cool example. Yeah, and I think people like, I really think you should do this more often in practice because again, like you're so sensitive to your sample size and you end up like just getting like over concluding in favor of like minuscule differences. They're sort of, it becomes this like, it's statistically significant, but not practically significant. So you can kind of control that using this C posterior framework. Okay, so our actual original motivation was more, you know, work a lot on mixture models. It was more this Gaussian mixture model. So let's say we have the mixture model. So then the idealized data are drawn from this mixture of you know, kernels. And so we have weights W1 through WK on the different kernels, F of verify I for the ith kernel. And then we put a prior on the number of components K, the weights W, and the parameters verify. Okay, and so then the relative entropy C posterior is approximated by this power posterior. And we could use you know, some sort of reversible jump or something, or we can kind of reparameterize in a simple way that allows just like regular Metropolis Hastings. There's a lot of different ways we could do computation here. So we just do something, and then let's go back to this example. And so this was the example before. So the truth is like, you know, an equal mixture of two skewed normals. And so here you could and using strategy 2, you could think like, okay, well then if I make the kind of asymptotic sample size 100, then if I kind of, and I could try to detect this by sampling from, you know, one rough way to check it would be to sample from skew normals or some other kind of non-Gaussian distribution, but that's not crazy non-Gaussian. That has some modest departure. And then I could plot histograms repeatedly for sample size 100 and then just look at it and then like, I can't really tell based on this histogram that there's a difference that these are non-Gaussian. And so at what point can you like tell based on looking at the histogram or even doing some test based on that sample size that it's non-Gaussian? And so maybe 100 seems to be reasonable in this setting. Okay, so then if we do that, then you know, here's the data distribution, and then the standard posterior, we end up getting, as I showed before, like as the sample size increases, we get more and more components, and then we end up taking these two mixture components and kind of breaking them up, kind of doing cluster splitting, and so that happens for the regular, but the for our alternative for our coarsened posterior, we don't get that happening. We get the right number. We get the right number of components. And this is there's been like at least dozens, if not 100 or something, uses of this in practice. Like Li Ma used it in a couple of papers. Other people have used this a lot to robustify clustering. It's become pretty popular because it's so easy. It's sort of like, I'm doing parametric model inferences. It could be mixture model, it could be something slightly different. And then, well, I don't, you know, the model's pretty good, but I don't quite trust it. So I'm just going to do a little bit of coarsening to try to robustify my inferences. That's become, you know, reasonably popular. It's so easy to do. Yeah. So here's another classic one, the velocity of galaxies in the Shapley supercluster. So the Gaussian mixture assumption is probably wrong, even though like you probably attack this with a Gaussian mixture model. And so now we can kind of try strategy 3. So that's this kind of, let's consider a range of alpha values and then get some heuristic. Okay. And then if we do that, now we try to have this range of alpha values. Then we can see like as alpha increases, we do get more and more components because we're sort of going towards the you know the regular case as alpha becomes really big. I mean that's the alpha equals infinity. That's the usual posterior, which is giving you like too many components, like enough components to like fit the data density well, but like too many components to actually interpret any of these components because you're like having a bunch of Gaussians that are right on top of each other. Whereas the coarsened approach does well here, and then we can use our heuristic to choose a good value of alpha. Yeah. Okay. Just go through running out of time, but just kind of flash up the theory, and then if we have any time at all, just kind of give a more interesting example, but maybe just flash up the more interesting example. So we have kind of two main theory results. The asymptotic form of the C-posteriors, which we use some asymptotics to justify the original form, and then also robustness of C-posteriors to actually show they're robust to perturbations in the data distribution. Okay. And so we have this model, theta is drawn from pi, and then we have the idealized x1 to xn, we're drawing IID from p theta, and then we have this R neighborhood size. Okay. And then the x1 to xn are sampled IID from some p naught. So that's just repeating the notation from before. Okay, so the asymptotic form. So let's let G of R be the probability that the neighborhood size is bigger than little r. We're going to assume that at the discrepancy between P of theta and P of naught, the probability that discrepancy equals R is equal to 0. So it's not like going to be equal to exactly 0. And the probability it's less than R is greater than 0. Okay, so then you have some notion of the probability of the discrepancy being small being positive at least. Okay, and so then now we're kind of building the C-posterior from conditioning on the event that this dn of x capital X1 to n, little x1 to xn, that discrepancy between those two, the idealized data and the true data, well, what's that going to asymptotically? Well, that's going almost surely to d of p of theta, comma p of p naught as n goes to infinity. So if that holds, so that we've just chosen our estimate of the discrepancy in that way, then the C-posterior converges to this form, which is proportional to the prior times this G of D of P of theta of P naught. Okay, and so we can show, and we can also show this form. I'll just kind of skip over this for time. And so in terms of robustness, the standard posterior can be strongly affected by small changes to the observed data distribution, particularly when doing model inferences. So that's the setting, one of these brittleness settings where we're particularly motivated to do C-Bayes. In certain settings, like a small perturbation, so you're using some model P of theta and then P naught like is close to P of theta, like it might not make much difference. I'm just estimating the mean or the covariance or something, some moments, and then I don't have this model model uncertainty issue, then then it might not be a big deal. But particularly in the setting of model uncertainty, we end up with a lot of sensitivity to the when doing these model inferences. So this kind of illustrates that, like as the discrepancy between P naught and P theta increases, this can have a big impact on the posterior. Okay, and so we get a robustness theorem. I can see that I'm pretty much out of time here. So I mentioned that this example in terms of mixtures, I would just note that I'd like to allow a couple minutes for questions, but I'll just note that this kind of problems also happen in other model selection settings. And so if we have autoregressive models of unknown order, it might not be first order, it might be second or third order. So you could think like, oh, I use a first order model, but it's actually just a bit misspecified. Then what happens asymptotically is I might just like make it like super higher order. And so, even though the first order model is really quite close approximation. And in linear regression, what can happen is we just, like, oh, you're really close to a model with like two good predictors, but we have all this other bag of predictors that are doing almost nothing, but we just keep adding them anyway, artifactually, as the sample size increases. And so we can also protect against that, which is a kind of beyond linear regression, a well-known problem. Like everything becomes significant as the sample size increases in a regression. That's well known. And so we can kind of protect against that as well. So I'll just not show those birth weight of infants. Yeah, we had some more cool examples, but yeah, I think I've said anything. I'll just stop there for questions.
Great. Thank you so much, David. That was brilliant. Do we have any questions in the audience? Jay, do you want to go for it?
Yeah, that sounds good. I don't know if it's a question or more like a half observation that I made over the duration of the talk. But one thing that strikes me is, David, you also mentioned it a couple of times. It's very awkward that the thing doesn't concentrate because normally, as you do Bayesian updating in particular, you would want to eventually learn everything there is to learn, and you want your posterior uncertainty to vanish. And it strikes me that it's not a coincidence that this stuff is particularly useful for model selection, basically, right? Like, I mean, if you look at the number of mixture components, I think of this as a model selection problem. And a lot of the Gibbs posteriors that we've also seen over the previous weeks, or that, I have also worked in and I'm quite partial to, I think they're much more concerned with parameter estimation, perhaps, than this approach would be. And so perhaps that's one of the reasons why is actually the lack of concentration is an advantage in one setting. And in the other setting, it's very conceptually and epistemologically confusing to not have concentration. So I indeed, I agree. If one found a way to do this adaptively, one could bridge that gap as well. So I don't know, it's not really a question.
I mean,
it's more
I think
something
it
that
is.
came
Yeah,
in my
no,
head.
I love the comment. I mean, I think we're all obsessed with, I mean, so I don't think it's like really a negative. It's just like we're so used to getting concentration and we love so much and we're used to like, oh, showing these frequentist asymptotic properties. But like, is that the right answer if you have model uncertainty? Maybe not. But then like, what do we say about it in that case? Like, can we come up with like other theoretical lenses? Certainly it would be nice to adapt if the model was correctly specified, but in reality, they never are. And so I think the lack of concentration is an appealing property that kind of protects you against some of these pitfalls that we get, particularly in large sample settings. And so, but how can we kind of better think about it and develop even theory lenses for kind of embracing the lack of concentration?
Yeah, I think one last comment, and I'll not take up all the time we have for questions. It could be interesting. I don't know if that's been attempted to look at this through the lens of pack base and see if that gives you any hope for helping to choose this alpha parameter for like adaptively, let's say, because actually pack-based does a lot of things that are kind of counterintuitive even from Bayesian perspective. You would normally actually have like a power posterior in the pack-Bayesian sense, where you don't actually scale the data with n. If you want a pack-based bound, you scale it with square root n. So you get these interesting interactions. I wonder if there's something to be made of that, but I haven't looked at it. Just some food for thought. I'll mute myself if there are other questions.
I have no idea regarding pack base. We definitely, that was not the route we were going when we had a couple of weeks of meetings about it.
I don't know if there are any more. We maybe have time for one more quick question, if there is one floating around the audience. Give a couple of.
And if anyone has questions after or complaints or thoughts or wants to collaborate on something, just email me, certainly. So.
Terrific. In that case, I think we might end it there. Thank you again, David, for a brilliant talk.
Yeah, thanks. I appreciate it.